Article 250.64e of the National Electrical Code, or NEC, requires that all metallic enclosures for electrical equipment be grounded. Article 250.70 requires that the grounding conductor for a service or feeder be connected to the grounding electrode conductor, or GEC, at the service equipment or disconnecting means. When installing a grounding electrode conductor, several factors must be considered to ensure compliance with the NEC. Firstly, the EMT conduit, being a metallic enclosure, must be grounded. Secondly, the number 4 GEC is the grounding electrode conductor for the structure. Thirdly, the GEC must be properly connected to the ground bus and the electrical panel. While it is generally recommended to use grounding bushings on both ends of a metallic raceway, it is not strictly required by the NEC in this specific situation. Because the GEC is connected to the grounding bus, the non-concentric knockout in a panel is considered sufficiently grounded. The installation is likely compliant with the NEC requirements. A grounding bushing is not necessarily required, and the panel end of the EMT conduit and a short number 4 jumper to the ground bar is suitable. The grounding electrode conductor must be sized according to NEC Table 250.66, which dictates the conductor size based on the size of the service entrance conductors. The GEC must be securely fastened to the grounding electrode, using methods outlined in NEC 250.70. For rods and pipes, this often involves exothermic welding, listed lugs, or reversible compression-type connectors. The path of the GEC should be as short as practicable and free from sharp bends or damage. The GEC should be protected from physical damage, as required by NEC 250.64b. This protection can be achieved through conduit or other approved means. The grounding electrode system can consist of several electrodes, such as ground rods, metal water pipes, and building steel. When multiple electrodes are present, they must be bonded together to form a unified grounding system. Metal water pipes used as grounding electrodes must be supplemented by an additional electrode, such as a ground rod, to ensure a reliable grounding path. The connection to a metal water pipe must be made within 5 feet of its entrance to the building, as per NEC 250.52 AON. Ground rods must be at least 8 feet long and driven into the ground to their full length, unless rock bottom is encountered. In such cases, the rod can be buried horizontally in a trench at least 30 inches deep. The location of grounding electrodes must be accessible and free from obstructions to allow for inspection and maintenance. The resistance of the grounding electrode system should be as low as possible. Ideally, it should not exceed 25 ohms. If the resistance exceeds this value, an additional grounding electrode is required, as per NEC 250.53 ATWA. A GEC must be continuous and without splices, unless the splice is made using reversible compression connectors listed for the purpose, or by exothermic welding. When running the GEC through metallic enclosures, such as conduit, bonding jumpers may be required to ensure electrical continuity. The size of these bonding jumpers should be based on NEC Table 250.102 current. The GEC must be identified along its entire length. This identification can be achieved through the use of green insulation or by marking it with green tape or paint at accessible locations. The GEC should be installed in a neat and workmanlike manner, following the guidelines outlined in NEC 110.12. All connections must be tight and secure, and the installation should be free from defects. When using a concrete encased electrode, it must be at least 20 feet long and encased in at least 2 inches of concrete. The concrete must be in direct contact with the earth. The GEC should be connected to the concrete encased electrode using an exothermic weld or listed connector suitable for direct burial. When using building steel as a grounding electrode, it must be effectively grounded to the earth. The connection to the building steel must be made at multiple points to ensure a low impedance ground path. The GEC should be protected from corrosion, especially in harsh environments. This protection can be achieved through the use of corrosion-resistant materials or by applying a protective coating to the conductor. The GEC should be installed in a manner that minimizes the risk of ground loops. Ground loops can cause unwanted current flow and can interfere with the operation of sensitive electronic equipment. The GEC should be routed separately from other conductors to minimize inductive coupling. Inductive coupling can cause voltage to be induced in the GEC, which can contribute to ground loop problems. A GEC should be inspected regularly to ensure that it is in good condition and that all connections are tight and secure. Any damage or corrosion should be repaired promptly. The GEC should be tested periodically to verify that the grounding electrode system is functioning properly. This testing can be performed using a ground resistance tester. The GEC should be installed in accordance with all applicable local codes and regulations. These codes may impose additional requirements beyond those specified in the NEC. The GEC should be installed by a qualified electrician who is familiar with the NEC and local codes. A permit may be required for the installation of a grounding electrode system. Check with your local building department for permit requirements. The GEC should be properly documented, including the size and type of conductor, the location of the grounding electrodes, and the results of any testing. This documentation can be useful for future maintenance and troubleshooting. The GEC should be installed in a manner that minimizes the risk of electrical shock. All work on electrical systems should be performed with the power off and with appropriate safety precautions in place. The GEC should be installed in a manner that does not create a fire hazard. All electrical connections should be made properly and securely to prevent overheating. The GEC should be installed in a manner that does not interfere with the operation of other electrical systems. The grounding system should be designed to provide a lower impedance path for fault current to return to the source. The grounding system should be coordinated with the overcurrent protection devices to ensure that faults are cleared quickly and safely. The grounding system should be designed to minimize the risk of voltage transients. Voltage transients can damage sensitive electronic equipment. The grounding system should be designed to provide a stable reference point for electronic equipment. This can improve the performance and reliability of the equipment. The grounding system should be designed to minimize the risk of electromagnetic interference, or EMI. EMI can disrupt the operation of electronic equipment. The grounding system should be designed to comply with all applicable industry standards. These standards may specify additional requirements for grounding systems in certain types of facilities. The grounding system should be designed to be flexible and adaptable to future changes. The system should be able to accommodate new equipment and changes in the electrical load. The grounding system should be designed to be maintainable. The system should be accessible for inspection and testing. The grounding system should be designed to be cost-effective. The system should be designed to meet the required performance criteria at the lowest possible cost. The grounding system should be designed to be environmentally friendly. The system should be designed to minimize the impact on the environment. Firstly, consider the service entrance conductor size to determine the appropriate GEC size from NEC Table 250.66. Secondly, ensure proper connection to the grounding electrode, using methods compliant with NEC 250.70. Thirdly, protect the GEC from physical damage as per NEC 250.64b, using conduit if necessary. Fourthly, bond multiple grounding electrodes together to form a unified system, as specified in NEC 250.50. Fifthly, supplement metal water pipe electrodes with an additional electrode like a ground rod, following NEC 250.53d2. Sixthly, ensure ground rods are at least 8 feet long and fully driven or buried in a trench if needed. Seventhly, aim for a grounding electrode system resistance of 25 ohms or less, adding electrodes if required by NEC 250.53 Atware. Eighthly, use continuous GEC without splices, unless using approved methods like exothermic welding. Ninthly, identify the GEC with green insulation or markings for easy recognition. Tenthly, install the GEC in a neat and workmanlike manner, adhering to NEC 110.12. The grounding electrode conductor plays a vital role in electrical safety by providing a low impedance path for fault current to return to the source, thereby facilitating the quick operation of overcurrent protection devices like circuit breakers and fuses. This rapid clearing of faults minimizes the risk of electrical shock, fire, and equipment damage. A properly installed GC also helps to stabilize voltage levels within the electrical system, preventing voltage fluctuations that can damage sensitive electronic equipment. By providing a stable reference point, the GC contributes to the reliable operation of computers, communication systems, and other critical devices. Furthermore, the GC helps to minimize electromagnetic interference, or EMI, which can disrupt the performance of electronic equipment. By providing a low impedance path for unwanted electrical noise, the GC reduces the amount of EMI that is radiated into the surrounding environment. Regular inspection and maintenance of the GC are essential to ensure its continued effectiveness. The conductor should be checked for signs of corrosion, damage, or loose connections. Any problems should be corrected promptly to maintain the integrity of the grounding system. Testing the grounding electrode system periodically is also important to verify that it is functioning properly. A ground resistance tester can be used to measure the resistance of the grounding electrode system and to ensure that it is within acceptable limits. In addition to the NEC requirements, local codes and regulations may impose additional requirements for grounding electrode conductors. It is important to check with your local building department to ensure that your installation complies with all applicable codes. When installing a grounding electrode conductor, it is always best to consult with a qualified electrician. A qualified electrician can help you to design and install a grounding system that meets your specific needs and complies with all applicable codes and regulations. By following these guidelines, you can ensure that your grounding electrode conductor is installed safely and effectively, providing reliable protection against electrical hazards. The importance of a properly installed and maintained grounding electrode conductor cannot be overstated. It is a critical component of any electrical system, providing essential protection against electrical shock, fire, and equipment damage. By taking the time to install and maintain your GEC properly, you can help to ensure the safety of yourself, your family, and your property. Remember to always prioritize safety when working with electricity and to consult with a qualified electrician if you have any questions or concerns.